Okay, so what are the energy eigenvalues of a particle in a box? So we have, let's say, we have a volume, a cubic volume with side length L. Well, the shape doesn't really matter, but for simplicity, let's just assume all of them are L. So what are the energy levels of a single particle in a box?
N squared by L cube.
For a single particle, it will be nx squared, pi squared, nx squared over L squared, plus pi squared, ny squared over L squared, plus pi squared, nz squared over L squared, multiplied by 1 over 2m. Well, the easiest way to remember this is if you just put the origin over here at 0, 0, 0, the wave function will be just sine of kx times x, sine of ky times y, sine of kz times z, and I want the wave function to be 0 also at the other end of the cube, so that will tell me that kx times L should be equal to nx times pi, ky times L should be ny times pi, and kz times L should be nz times pi. And there's also an h bar squared. So these are the possible energy eigenvalues. Now, what are the possible values of nx, ny, and nz?
Sorry?
What are the possible eigenvalues values of nx, ny, and nz?
Odd ones, sine complex.
Well, 0 is not there. So let me give you your one homework problem. Now here you see what I am assuming is that fixed boundary condition, the wave function is 0 at both ends. But let's say that you have periodic boundary conditions. Well, you will see that the possible values of kx will be different now. And the energy expression will look different. Nevertheless, you will get the same answer. So that is something I would like you to see. Okay, so of course, this is just one particle. Its energy is given by h bar squared pi squared over 2ml squared times n squared, where I just call this nx, ny, nz vector as my point.
And the denominator is m, right? Mass, not
M.
Ah, okay. This looks like an m. Okay.
Well, I apologize for my handwriting. Sometimes even I fail to read it correctly, but that is M. So this is the energy of a single particle. If I have many particles, basically the total energy of the system will be just the sum of the energies of each one of those particles, h bar squared pi squared over 2m. Well, instead of L squared, let me write the volume raised to the power 2/3 times Ni squared. Well, for each particle I have Nx, Ny, and Z values, and they might be different for different particles. And of course here I'm summing over these can take values 1 to up to infinity, each one of them. Now, to see how we will proceed after this, okay, so before that, let me write this in a slightly different form. You say h bar squared, pi squared, 2m and v, they're all constants. So this tells me that Ni squared should be equal to 2m over h bar squared, pi squared, e times v to the 2/3. So we are interested in calculating the number of microstates, which in principle will depend on V, N, and E. But you see, I already see here that E and V, they only appear in that combination. I have to find all the number of all possible integers that will satisfy that equation. The solution will not depend on E or V separately. It will depend only on that combination. So this will be equal to some function of N and E times V to the power 2/3. I haven't yet calculated it. I don't know what this function is, but I already know that it doesn't depend on E and V separately. It depends on that combination. Now I know I can say the same thing for the entropy. Entropy will be a function of E and V to the 2/3. Well, remember the S is the dE over T plus P over T dV minus mu over T dN. So 1 over T is ds over dE, keeping V and N constant. Well, this is equal to the derivative of our entropy expression with respect to its second argument times the derivative of E times V to the 2/3 with respect to E, of course keeping V and N constant, which will be just V to the power 2/3 times the derivative of the entropy with respect to its second argument. Well, P over T, on the other hand, is the derivative of the entropy with respect to V, keeping E and N constant. Well, V appears only in the second argument, so again, it's the derivative of entropy with respect to the second argument times the derivative of E times V to the 2/3 with respect to V, keeping E constant. Well, this will be 2/3 V to the 1/3 times E times the second derivative, the derivative of the entropy with respect to its second argument. Well, you see, the first relation, well, this is my second term. Well, the first line already tells me that the derivative of the entropy with respect to its second argument is nothing but 1 over T times V to the power 2/3. Well, these T's I can cancel on both sides, so this is 2/3 E over V. Oops, sorry. So the energy of the ideal gas is 3 over 2 times PV. Well, we didn't derive the ideal gas law in this treatment, but if you use that, this is also equal to 3 over 2 N KB times T. So some results that we already knew about the ideal gas. And just keep in mind that I didn't yet do any computation, any significant computation. Just making the observation that entropy depends on that combination E times V to the 2/3, it allows me to calculate the relation between energy and PV. And in an adiabatic process, I already know that E times V to the 2/3 is constant. But this is 3 over 2 P times V to the power 5/3, this is which is constant. So I already have the adiabatic constant without doing any complicated computation. So any questions up to here? Okay, then let's go back to this equation. So we would like to count the number of integers ni which satisfy this equation. Well, to see how we will proceed, let me just consider.
Can I ask a question?
Sure.
So previously we said the energy should be dependent on the number of degrees of freedom, right? So this result is true only for monatomic gas. Because 3/2 is coming from F/2. F is the number of degrees of freedom. So if I have diatomic case, I would have.
You see, the question is, what is your expression of energy?
Right.
If I have a diatomic gas, it will be rotating, it will be vibrating, I will have additional quantum numbers.
And again,
The energy, this epsilon will have a different expression, and hence all my successive treatment will be should be modified.
what guarantees that the other degrees of freedom are coming into this expression as a quadratic degree of freedom?
Okay.
So I don't know how to model it. I didn't solve a single question where we had a particle in a box with a diatomic gas. So I don't know the energy.
Well, see, for a diatomic gas, what will we have? We will have the vibrational modes. So what is the energy of a harmonic oscillator?
Kx squared.
Hmm?
Okay, so it's quadratic.
H bar omega, let me say m plus 1/2. So now I also have possible different values of m, which I need to take into account when I'm calculating the number of microstates. Now there will be rotations.
Yeah. What's the rotation?
1/2 I h bar squared L plus 1. No, L squared over 2I.
Yeah.
Now, we will, at the moment, we are just trying to get a feeling of what is going on here. What is our phase space, etc. We will be studying all these properties. What happens when we have vibrations, what happens when we have rotations, how we can treat them in classical physics, how we can treat them in quantum physics. We will do that explicitly. But this is what we will call the microcanonical ensemble. We are fixing the energy, and I'm asking the question, what are the number of microstates having this much energy? E is fixed. And hence I need to find the integer sets that will satisfy this equation. If I want to treat the vibrations and the rotations, the canonical ensemble will be much easier. That we will do that, the vibrations and rotations all also for in canonical, microcanonical, and grand canonical ensemble. They will come. Okay, if we continue along this line, let me just take two of these. Let me look at the integers n1 squared plus n2 squared. This is equal to 2m over h bar squared pi squared e v to the 2/3. And each one of these ni's will be 1, 2, etc. So if the horizontal axis is n1, the vertical axis is n2, I have 1, 2, 3, 4, 5. I have this grid over here. And each one of these intersection points is a microstate of my system. Now what I want, well, this equality just gives me a sphere. By the way, I don't have any microstates on the other quadrants. I only have microstates in the first quadrant. In your homework, you will have microstates in all the quadrants. What do I want? I want to count the points passing through a given circle. Now, this is the equation of a sphere, or in this two-dimensional case, a circle. How many points lie on this circle? Now, if you look at this two-dimensional case, you will immediately see that the number will be very fluctuating, wildly fluctuating. There might be some radii for which it doesn't pass through any point. There might be some other radii where it will be crossing 2 states, and others 3 states, 1 state. It will be all around the place. Well, if you go to higher dimensions, the fluctuations will be even more wild. It will be the graph will be basically a broken line. It won't be well, not even a broken line. It will be just ups and downs, almost some of Dirac deltas. But saying that we have a definite energy is not that physical for various reasons. One of them is, well, how can you make sure that a given state has a definite and this energy, let's say 5 joules? When you make experimental measurements, well, you will be measuring the energy with some uncertainty. And so you will always have some error bars. Secondly, well, if you want to keep the energy fixed, you have to isolate your system. No physical system is really completely 100% isolated. There is always some kind of an interaction. And hence there will be energy fluctuations in your system. So that will also bring down additional uncertainties in the energy. So your macro state doesn't really have a fixed value of energy, but rather a range of energies.
What would we measure with a thermometer or temperature?
That's a temperature. That's a different thing. Here, I'm not measuring.
For ideal gases in a root mean square velocities of the gas directly proportional to temperature. So you get a definite value with a very small, very small fluctuations.
In temperature, you mean?
In temperature. Isn't that a proxy for energy? Because energy is the root
You see,
square of the...
Here, there's no temperature. We are talking about energy only. We will define the temperature. You see, here, we are deriving the temperature from other properties.
Also, secondly, last time you said we'd find the system in its most probable configuration and fluctuations away would die rapidly. Why doesn't that produce a definite energy state here, or a most likely energy state here?
Sure, even in that case, there will be an uncertainty in energy. Small, but it will be
like 1 over root n.
Now, the probability of fluctuation is 1 over root n. But still, if you want to have, I don't know, a fluctuation that is of the order of 0.1%, well, so what? That will happen.
Okay.
So what we are actually interested, what we should ask is the number of microstates within such a shell. This will also have a more smooth behavior, so when we talk about derivatives, it will have a meaning. You see, if we don't do this, we cannot talk about derivatives. So we have to do other things rather than talking about derivatives. And in fact, this is why we go from, instead of obtaining omega E, what we do is we calculated sigma E plus, let's say, delta E over 2 minus sigma E minus delta E over 2. This is what we calculate. Well, this is basically, the sigma is the number of states having energy E plus delta, energy less than E plus delta E over 2. That is the number of microstates having inside the larger sphere, inside the sphere determined by the outer surface of this shell, minus the number of microstates that are inside the sphere determined by the inner surface of this shell. So if I take the difference, I only get the number of microstates in my shell. And this will be equal to delta sigma by delta E, derivative of sigma with respect to E multiplied by delta E. Well, in fact, we had already said that this is basically, for all practical purpose, well, if you like, let me divide by E multiplied by E also. But for all practical purposes, logarithm of omega will be equal to logarithm of E times d sigma by dE. Now, let me also add logarithm of delta E over E. You see, you can measure the energy very precisely, but the precision you will get will be, I don't know, 1 part in 10 to the power 4. How precise can you measure the energy of a system? Do you have an idea? Or some other experimentalists? Some other experimentalists? Well, 1 part in 10 to 4, that is better than you can do, or you can do better than that?
No, I can't do that.
Okay, 1 part, this fractional uncertainty in the energy is more than 1 part in 10 to the power minus 4. But you see, this number, it just tells me that this number is minus 4. Whereas this number will be of the order of 10 to the power 23. So just forget that delta E over E term. It won't affect the entropy. In fact, this is what we use also on Monday. We calculated sigma, took the derivative. In fact, the derivative was mainly dividing by E. That is also what we will do here. So now I'm kind of converting my problem.
Can we say what we wrote in sigmas is approximately a total sum of moving averages?
What do you mean by total sum of? Yeah, probably. But then I need to divide. Then I need to say, what do you mean by moving averages? We have to discuss that. Yeah, no. I would rather not say that, but probably you can say that. Now let's go back to here. What I would like to calculate now is the number of states having energy, well, the number of microstates satisfying this inequality. Integer sets, n1x, n1y, and 1z, and 2x, and nz. So these are the quantum numbers of my system. I want to calculate this 3 antiples, which will satisfy this condition over here. Now, to see how we can do that, let's go back to this two-dimensional, greatly simplified example. Let me imagine squares such that squares of side length 1, such that each one will contain at most 1 point. So I will have a square here, another square here, another square here. Etc. So in higher dimensions, it will be just a unit cube or unit whatever volume you have, unit 3n dimensional cube. So if I want to count the number of points, it's enough for me to calculate the volume of this sphere, of this 1/4 sphere, and divide it by 1. It will give me approximately the number of microstates inside my sphere. Why 1? Well, that is the volume, or in this case, the area of each one of those squares. Basically, I'm finding an approximation for the number of squares in this area. Well, but since each square has 1 state in it, it's just the number of states.
Density of states?
No, number of states.
But we divide it through the total volume. Oh, okay, we found the number by dividing. Okay, yeah.
So now we have basically changed the question to how we can calculate that volume. Well, the volume, I'm sorry. I have to sum over 1 over each one of the points such that sum of ni squared will be less than or equal. Let me give this a new name, E star. E star. This is what I'm trying to calculate. Well, let me write it as an integral. Well, the volume is just the integral of the volume element in 3n dimensional space of my region, which will be the integral over dn. Well, let me just call this n1 up to n3n, this set. The integral over n1, the integral over n2, the integral over dn3n. Of course, these integrals all start from 0. And it will go up to this boundary is sum over ni squared is less than or equal to E star squared. No, E star, sorry, not squared. Well, let me kind of change this. You see, N1 or P1 is H bar times K1, which is H bar times N1 times pi over L. Or H bar pi over L times N1. Of course, this is correct for all the momenta. So I can make a change of variable. So sigma e is actually, instead of integrating over ni, I can replace ni by L over H bar pi pi. So sigma e will be L to the power 3n. Well, there is a factor L from each one of the ni's. There are 3n of them. Divided by pi h bar to the power 3n. Integrated over dp1 or the 3n dimensional momentum integral. Momentum starting from 0 up to some value restricted by the constraint that sum over pi squared should be less than or equal to e. Well, V is no longer over there. Remember, my constraint is for Ni. I have Ni squared should be less than or equal to 2m over h bar squared pi squared E times L squared, or Pi squared should be less than or equal to 2me in terms of pi. Well, let me again change this slightly. This is d3 and p from 0 up to some value. d3 and q, because that is L to the 3n. But now I would like you to remember what we did on Monday. We started by saying that sigma e is divided by pi h bar to the 3n. Sigma e was d cubed d to the 3n p, d to the 3n q. This was the area of the hypersurface in phase space, and we said that, okay, let's divide this by omega 0 to the n. Now, if you compare this, you find that omega 0 is pi h bar to the cube. So do you remember anything from your statistical thermodynamics course? Okay, I can tell because this is the wrong answer. Okay, there are a couple of things you should always remember. One of them is this is not pi h bar, it's 2 pi h bar. Because there is a difference between this classical integral and this quantum mechanical integral. You see, when we were looking at the classical physics, we said that the coordinate momentum p can be both positive or negative. They are not restricted from below by 0. But you see, if you go back, that is why I insisted on writing the lower limit as 0. Well, I can remove that. I can also take into account the minus p region. Or if you want to go to here, I can just take into account the other 3 quadrants. But if I want to do that, in this 2-dimensional example, I just calculate the number of points and divide by 1/2 squared. Well, that is the same thing as allowing p to take negative values, but dividing each momentum integral by 2, because positive and negative momentum contribution will be practically identical. So if I remove that 0 lower limit, this is equal to d cubed d3n p d3n cube divided by 2 pi h bar to the power 3n. So here I have 2 pi, or h to the cube. Well, this is basically something we would expect also from the uncertainty principle. The uncertainty principle tells me that the maximum you can localize the state of a particle in position and momentum is somewhat given by h, the Planck constant. So we would have expected from the start that omega 0 should be h cubed with some overall factor. But it wouldn't allow us to calculate what that factor is, but this explicit computation tells us that that factor is just 1. So now, at least for an explicit case of ideal gas, we know that even if we treat the problem classically, the volume for each particle in phase space is just h, or 2 pi h bar. Okay, this 2 pi h bar is one factor that you should always remember. We will always put it there. So any questions? Well, let's see what ensembles are. This is a tool that we will be using again throughout this course. In fact, we had already used this concept of the concepts brought by ensemble theory in our previous derivation, but here we will just have a formal definition. Now, we have already talked about the phase space, P and Q. If we have n particles, the horizontal axis is actually just 3n dimensional. The vertical axis is also 3n dimensional. If you look at the microstate will be given by the position and momentum of each one of those particles. So let's say that at a given instant, my state will be somewhere over there. If I follow the evolution of my system, the momenta and the position of the particles will change. They will be colliding with each other, and hence their momentum will change. And since they are just moving around, their position will also change. So if you just follow your system basically will follow such a trajectory in phase space. Well, I mean, if you think of quantum mechanics, you see we will be dealing with both classical, we will be treating the same systems both classically and quantum mechanically. This is the classical description Well, if you try to generalize this description to quantum mechanics, well, you will see a problem. Because for the quantum mechanical system, we said that, okay, the microstate is determined by these numbers, nx, ny, and z, those integers. But if the system has a definite energy, the system just does not change. It is fixed. So, well, there is no such trajectory in phase space. Quantum mechanics tells us that the system is just a point. Now, we will develop quantum statistical mechanics later on in a more formal manner, but even for a quantum mechanical system, this trajectory will still make kind of a sense, mainly because of the uncertainties I mentioned, because every system basically interacts with the environment. So no realistic system is, in fact, an energy eigenstate. So they will be constantly changing. In fact, since we are also looking at large systems with large degrees of freedom, the separation between the energy levels will also be negligible. So it's almost a continuous spectrum. So even a very small impact will change the energy state. And hence, quantum mechanical system will still have kind of such a trajectory. But for the time being, we will stick with the classical system. So what I would like to measure, now we should ask ourselves that question. So how long does a measurement take? So who are experimentalists here? Okay, you, I know. All other theoretical physics? Are you also working on theoretical physics? Well, I will also ask you questions, so if you are afraid of receiving questions. Okay, so how long does a measurement take?
Highly depends.
Give me a number.
For example, 2 seconds.
2 seconds, okay. 2 seconds. Is it a long time or a short time?
Long time. Long time.
If you want to say that a time is long or short, you have to say compared to what? 2 seconds for microscopic interactions is a huge amount of time. During that time, the system will be changing all around the region. So what you are actually measuring when you make a measurement will be an average over time. So a measurement will be some kind of an average over time. Well, let's see. In theory, rather than taking averages over time, we prefer to talk about what happens at this moment. So let me just imagine that instead of looking at a single system at different times and following its trajectory, let me take copies of the same system. So one copy here, another copy over here, another copy here. So I take my system, I take identical copies of my system. Of course, in practice, I will just pick them up randomly. But since it's random, each one of those will be at a different point in this trajectory. So I will just pick up those many copies of my system. They will correspond, if I don't do something stupid, they will correspond to the state of my system at different times. And so these many copies of my system is what I call the ensemble.
Isn't the action of an operator on a vector in Hilbert space a measurement? Isn't that how we represent measurement? So the measurement of momentum is the action of the P operator on a...
You see, when I say measurement, your friend just goes to the laboratory, takes the device, and makes an actual measurement.
Right. No, I'm asking how do we represent a measurement mathematically? Because what you're describing as an average over time would then be, would be expectation value, right? Of P would be the thing that we get, right?
Yeah, time average. Time average will be the expectation value. Well, the time average will also be the ensemble average. Well, what do you mean by an ensemble? By the average of something? Well, I have, for each one of those points, I can measure something. Let's say Fi. I will be summing them over my ensemble and divide by the number of copies in my ensemble. This is what I will call the ensemble average. And in fact, this argument over here basically serves to show that this ensemble average is actually equal to the time average. And of course, I should repeat that we are looking at systems in equilibrium. So this T0, it doesn't really matter what you choose as your starting point. The system doesn't change. Macroscopically, the system doesn't change. And so the time average will be actually equal to the ensemble average. Well, this basically allows me to look at the system from a different perspective. Rather than look at the evolution of my a given system in time, I can ask myself the question, how does my ensemble evolve in time? In equilibrium, it shouldn't evolve. But I can always ask the question, let me just take many copies of my system, whether they are in equilibrium or not, I don't care. I have a given system, I take many copies, and I show them in all those copies as points in my phase space. So I have many points in my phase space. Then I can talk about the density of points in my phase space and ask you the question, how does this density of points in phase space evolve with time? And that evolution should be 0. Anyway, but that will come later on. Any questions? Let's give a break for 10 minutes after. If you have any questions, you can ask now. Yes?
The time average and the ensemble average. Can we say that this is equal to the measurement result?
Yes.
At the point of equilibrium?
Well, since we are looking at equilibriums, we will be looking at equilibrium systems. Your measurement result will be the same as the time average of your measurement result. Well, basically because your measurement will not change. It shouldn't change because it's an equilibrium system. And which will be the same as the ensemble average.
Looking only at the phase space, how can we tell about the time propagation?
We will see at the beginning of next hour.
Have we defined these ensembles yet?
Well, you see,
Canonical, and so on.
if you look at this point, well, this point over here, that point at this instant is moving in this direction. If I look at this point, that point is moving in this direction. And the motion of these points is determined by Hamiltonian mechanics. So that is what we will use here. Yes, Adil.
Have we defined microcanonical, grand canonical,
No,
and so on?
not yet. I'm just talking about ensembles now. Okay, so let's give a 10-minute break and we will continue.